So what I hope you figured out in the last one is that this is how that function came out. And what does that look like? That looks like an XOR, right? That looks exactly like an XOR. It is an XOR, an exclusive OR. The key thing is, for any function that you define, there is some combination of and, or, and not that we can use in order to create that same output. So remember, what we've been saying this whole time is a function is whatever you choose. So, you have a domain and a range, and that range could be anything. This theorem, right, this is Theorem 1 from your book. This theorem states that no matter what that output is, there is some combination of ands, ors, and nots that can give you that. And let me show you an example of that right now. All right, so this is our defined function here, right? P, Q, and R are our three tuple inputs, right? And F is our function, and F is 1 in these cases and 0 in all the other cases. So how can I construct a series of ands, ors, and nots that will always produce the same output as this function F? We go line by line. So in this case, the output is 1 if the input is 0, 0, 1, right? So what that is, make sense? So not P is 1, not Q is 1, because P and Q are 0 here, right? So when we negate them, we get 1. So this is saying 1 and 1, because R is 1, and 1. Now, in a lot of cases, you might write this as not P and not Q and R, right? But that is incorrect, because we should be using our parentheses to make it clear which order we're doing things in. It doesn't matter if I do this side first before, or do this side. It doesn't matter on the output, but we should always be clear, right? So that's why I'm putting these parentheses here, all right? So first thing that happens is we negate Q, right? And it with R, take the whole thing, or negate P, and it with everything. In that case, the output is 1. This output will be 1. And let's put a big pair of parentheses over the whole thing. Agreed? Agreed. In the next case, here, we have not P, Q, and not R. So let's go ahead and put the parentheses around our nots. We're going to keep the same kind of order there. So in this case, so essentially, this is I'm trying to explain it, but it's really simple. Everywhere you see a symbol, or see a 0, not that. Everywhere you see a 1, that. So that's it. And then the third case is down here. And we have, in this case, it is just P, Q, and R. So in any of those three cases, the output will be 1, right? And in each of these three formulas, the output will be 1. So what do we have to do then? We join them together. Imagine that this is all written on one giant line. I can't make it fit and make it easy to read. But you could see this written on one line, right? It's the exact same thing. That's it. That is how, if I give you a truth table which tells you the function, you can always use a combination of ands, ors, and nots in order to build it up. Now this is called, in your book, this is called the conjunctive norm. In the CS51 class, we call this the max term, right? Those essentially mean the same thing. The key thing here, well, the two words I want you to focus on, conjunctive. Wait, scratch that. I'm wrong. It's the disjunctive norm, right? Disjunctive because your big terms are ORed together. Norm because it is the norm. That is, it is a Boolean equation that expresses this that anybody could generate. There are probably 30, 40, a million other Boolean expressions that will also come out to have these same results. But they might be much longer and more complicated, or they might be shorter and simpler. But there's no algorithmic way based upon the truth table to figure out what those are. With the norm, you know, if I give this to everybody in the class, you should all come up with the same answer. Now, what we're going to learn later on in this course are theorems for reducing these, right? And two people might reduce it different ways and come up with different answers. But to get the norm, everybody should be on the same page, okay? So that is how we take any function as defined by a truth table and generate, using ands, ors, and nots, its Boolean equation. Okay, now there's another way to express this, which is called the conjunctive norm, also called the min term, and I'm going to show you how to do that in a second. But before you understand, first I want you to know why it works, and it works because of something called De Morgan's law, right? And De Morgan's law, they don't call it De Morgan's law in your book, which I don't understand, but it's based upon this one statement, this truth. P or Q or R or whatever all the way to T is the same as not P and not Q and not R all the way to T. Those two are the same. They don't seem like they'd be the same, but they are. Look at it like this. If P or Q or R, the only way that this can be 0 is if all of the inputs are 0, right? Because we're ORing them together. So the only way that the whole thing can be 0 is if they're all 0. If any of them are 1, then the whole thing is 1, right? The only way that this can be 0 is if everything inside the big parentheses is 0. Agreed? Because is 1, excuse me. Right? Because we're going to negate it, so everything inside the big parentheses has to be 1 for the whole thing to be 0. The only way for everything inside the parentheses to be 1 is if each value, each variable, is 0, because we're negating each variable and ANDing it with all the others. So if P is 0, Q is 0, R is 0, all the way down to T, right? Not 0 is 1 and 1 and 1 all the way down. And them all together, we get 1. Negate that, we get 0. So all ORed together or not, and then all the variables negated together, complemented. That's De Morgan's law. That says those two statements are the same, which is very counterintuitive. But are you with me? So then the question is, how do I get how do I generate the conjunctive norm from this? Well, everywhere I was looking at a 1, now I'm looking at the zeros. And yeah. So I'm going to say, so this is one of the lines. The other thing is, instead of being the negation and ANDing them together, I'm going to use, for zeros, I'm going to use the actual, wherever there's a 0, I will use the identity. Wherever there's a 1, I will use the negation, and I will OR them together. So in this case, I'm going to say P or Q or R, and don't forget we have to put those in the proper parentheses, and then I'm going to go down here, and this says P or not Q or not R. And then for this one, this says not P or Q or R. And on down the line. All right, so this is the, and then all of these will be ANDed together. I'm not going to do the whole thing. It gets kind of long. So the question is, should you use the disjunctive norm, right, the max terms, or the conjunctive norm, the min terms? And the answer is, you'll do whatever I tell you to do. Really, you'll do whatever the assignment says. In reality, which one would you choose? Which one would I choose? I'd choose the shortest one. So since there are only 3 ones here, I would choose the disjunctive form. If there were only 3 zeros, I would choose the conjunctive form, right? The key thing is this is the same as this. They're exactly the same. It's just one, they produce the same output. And I don't expect you to totally trust me on that, but play around with it. Try it. It'll work out. Okay? So that is Theorem 1 from Example 6. If you have any questions, ask them in the forum below.